Tom Wildrick has over 40 years' experience in manufacturing, including 30 years in plastics and PTFE. Tom's manufacturing experience covers a wide range of capabilities, including technical sales support, estimating, production planning, and process engineering. He is currently in an estimating role for Plastomer Technologies. Tom, thank you for joining our Global Spec E event.
Thank you, Jim, and welcome to the listeners out there. My presentation today will be on the polymer polytetrafluoroethylene, or PTFE for short. We will discuss the many properties of polytetrafluoroethylene, PTFE, and then go into the specific industrial applications, some of the commercial applications as well. PTFE is used in a broad range of industries, from offshore to outer space, from the impeccably clean conditions of an operating room and semiconductor processing facility to harsh environments such as the chemical refinery industry and the Alaskan pipeline. We will then look at the PTFE products and how this Teflon is processed. But first, let's look at a brief history of PTFE. PTFE was discovered by Dr. Roy Plunkett, who worked for E.I. DuPont, in 1938. Dr. Plunkett was actually trying to develop a new refrigerant when, at the end of his experiment, he opened his test chamber and noticed a white waxy substance clinging to the walls of his chamber. This white waxy substance became known as PTFE. Well, I don't know how his refrigerant experiment worked out, but this white waxy substance became quite the discovery. It was trademarked by DuPont in 1948 under the name of Teflon. For the first 10 years of its existence after its discovery, it was used almost exclusively by the U.S. government, notably the Manhattan Project, where it was used to coat valves and seals. After 1948, it went public, so to speak, and is now used in, like I say, commercial and industrial applications to the tune of roughly 60,000 tons per year. Let's look at some of these properties of Teflon, PTFE, and I'll go through them quickly and then we'll go back and look at some of them in more detail. PTFE has a low coefficient of friction. Glass, for example, has a coefficient of friction 25 times that of PTFE, and I usually think of glass as being fairly slippery. PTFE also has high temperature resistance. It has an operating temperature of up to 500 degrees Fahrenheit, but also on the other extreme, it can be used at temperatures as low as 450 degrees Fahrenheit below. PTFE is chemically inert. It is impervious to almost any chemical. It is impervious to ultraviolet light or just about anything else that Mother Nature can throw at it. PTFE is non-conductive, and it also has excellent dielectric properties. This makes PTFE an excellent insulator for wiring. PTFE has high purity characteristics, used in the operating room and used in semiconductor processing equipment. PTFE has excellent malleability or flexibility, and it also has low flammability, which is related to its high temperature resistance. Let's look now at some of these in more detail. I'm probably like most people, and the first I heard of Teflon was as a non-stick coating put on cookware and baking pans. Later on, PTFE was used to make dental floss, and it's very popular for that application. Chances are the paint nozzle, your electric spray paint nozzle, uses a PTFE nozzle to keep it from clogging and make it easy to clean. But PTFE also has many industrial applications for use in this low coefficient of friction characteristic. Seals, very important for reciprocating and rotating seals to have a low coefficient of friction to reduce drag on and less energy is used. Another application here is on bridge sliding pads. This is critical. This is something I didn't know before I get into this business, but the span of a bridge and the pillar of a bridge are not really connected. They're sandwiched in between a Teflon sliding pad. This is to allow for thermal expansion and contraction so that the bridge won't scaffold or separate during cold temperatures. Another characteristic of PTFE is its high dielectric strength. This is very important for electrical wiring, where it will not escape, the electricity will not escape the PTFE. One product that I find interesting is a little grommet made out of PTFE that is plugged into the exhaust manifold of an automobile. This grommet holds the CO2 sensor. This high dielectric strength allows the impulse to go back to the car's computer. The CO2 grommet, because of the high temperature of the exhaust manifold, it won't break down, being made out of PTFE. Very important properties to make this grommet work and function as it should. Another situation where this high dielectric strength property comes in to play is in electrical wiring, both wrapping the wire and also wrapping the wiring harness. Both Boeing and Airbus are huge consumers of this product. The Boeing 787 Dreamliner, for example, has over 50 miles of Teflon-coated wiring throughout its aircraft. The next feature I would like to talk about is the fact that PTFE has excellent malleability and flexibility. This is ideal in critical sealing applications where the PTFE will conform to the surface. If it's not quite perfect, the PTFE will form into that surface. I want to show you an application of this. This is a Chevron V packing set. The V's act as wedges against each other so that when there's compression in this direction, the V's expand outward and inward against the rod and the shaft, creating an effective seal. Another example of this flexibility of Teflon that's very important is in Teflon seal tape. This is the tape that the plumbers use and people around the house use all the time to wrap their pipe. This has taken the place of a liquid goop that plumbers used to use. And it's very effective. Because of the flexibility of PTFE, it conforms perfectly to the profile of the thread so that the mating thread can be put on and provides an effective seal. Pump diaphragms. This is a thin membrane of PTFE that vibrates several thousand times a minute, creating a pumping action. The PTFE, because of another feature I will talk about in a minute, does not break down under the harsh chemicals, but because of its flexibility, is allowed to flex several times, thousands of times a minute without breaking down. I want to talk about a product called expansion joints, also flex couplings. This is a PTFE accordion-like bellows that is used to separate two sections of rigid pipe in a chemical refinery, as you're seeing here. This is critical for thermal expansion and contraction so that the pipes don't fracture and cause a catastrophic failure. Also, if the pipes are misaligned somewhat, the PTFE expansion joint or flex coupling will take up that misalignment and allow for the leak-free transfer of liquids through the pipeline. Swivel joints used offshore, attached to the mooring, the fixed mooring, and also attached to the tanker on the other end, transport crude oil from the bottom of the ocean floor into the tanker. These PTFE seals, metal energized seals, have to have the malleability and the flexibility so that they do not fail and do not leak. Switching gears a little bit, I want to talk about the high purity applications of PTFE. As I mentioned before, it's used in operating rooms. They are used, PTFE implants, things like artery stents are used by surgeons to open up and repair arteries. PTFE patches are used to repair a hole in a baby's heart. Obviously, has to have high purity applications where absolutely no contamination is allowed. PTFE will not contaminate any substance that it comes in contact with. Another application using this high purity characteristic is in the processing of semiconductor wafer processing equipment. This is a clean room condition where absolutely no contamination is allowed. Many products are made out of PTFE used in this type of equipment, and PTFE is chosen because of its high purity characteristics. It will not contaminate anything that it comes in contact with, nor will anything that it touches affect the PTFE. And that's the next property I'd like to talk about. These are some of the products that you see here that are made for strictly the semiconductor industry. They're all virgin PTFE products. And now we will talk about the one very important property of an overlooked property of PTFE, and that is its chemical inertness. PTFE is impervious to virtually any chemical that it could come in contact with. This makes it excellent for sealing applications where the PTFE will seal off caustic fluids and chemicals from critical pump component, for example, or critical valve components. The most important aspect of this is that it can be used for virtually any application. With any liquid going through it will not be affected by the PTFE. One such product I'd like to mention again are the pump diaphragms. We talked about the flexibility of the pump diaphragms and how they're able to reciprocate several thousand times a minute. Well, they're pumping sometimes very caustic chemicals, and because they're made out of PTFE, they will not break down. You're seeing on your screen an example of a PTFE gasket with metal embedded in it. The metal used as a stiffener to, if you're bolting it up between two sections of pipe, the metal will keep the PTFE from extruding out, whereas the PTFE will protect the metal from corrosion. I'm showing here a spring energized seal, same concept. The PTFE will protect and seal. The spring energizer inside will help in the sealing process. PTFE protecting the seal from corrosion. Now let's take a few minutes to talk about PTFE products and how it gets to be made, some of these products I've been talking about. This is an example of PTFE resin as it comes from the manufacturer, such as DuPont. In its raw resin form, it's a white, waxy substance, sort of the consistency of flour, kind of looks like it and feels like it. If it's not to be blended with any other compounds, it is now ready to be processed into a geometric shape. And from the geometric shape, then it could be machined or formed into other products, as we've been looking at. Geometric shapes to include sheet, plate, cylinders, rods, tubing. We'll look at some of these in a little more detail. The compression molding process is used to make sheet and plate, PTFE plate, also shorter length cylinders, large diameter cylinders. In this process, the PTFE resin is put into a steel mold, thick-walled steel mold. If we're making a tube, there will be an inner core made out of steel and an outer core made out of steel. PTFE will fill in that cavity, be capped off with end rings, and then put into a press and pressed at 3,000 to 4,000 psi. Once that process is finished, it can be then taken out of its mold. It will have the integrity not to fall apart. It's still fairly fragile because it hasn't not been sintered. So caution must be taken. If it's dropped, it'll break, for example. But from there, it's put into an oven and taken up to 700 degrees. This doesn't actually melt the PTFE. That's why it can be free-sintered. It doesn't have to be in its mold as it's being sintered. But it does get to a gel state. It's then slowly cooled back to room temperature. When it gets to room temperature, then it is ready to be machined. We're somewhat limited as to the height or the length of the cylinders that we can do, because as this PTFE is being pressed, it has to be in a large steel cylinder, thick-walled cylinder. The tooling gets rather expensive. And it usually, we're talking about lengths of 12 inches and less with this process. If we need longer lengths, as in the case of rods and tubing, this usually is done by the ram extrusion process. In this process, PTFE cannot be used in this form because it's a little bit cakey, maybe you can see that, and it would cling to the sides of the mixing bowl. So it is first pelletized, put into a mixing bowl, and a ram pushes PTFE down into a barrel if we're making a rod, or into a barrel and over a mandrel if we are making tubing. As each successive charge goes down into the barrel, eventually that first charge will get down to the heating zone. Heating elements are attached to the barrel, heating the PTFE up to the 700 degrees. As that charge then moves past the heating elements, is centered, gets down into the cool section of the barrel where it cools enough so that it comes out the bottom of the barrel, then it is ready to be cut off at whatever length. Usually about an 8-foot length is desirable for a lot of industrial applications. And it too then is ready to be machined. Now, machining a PTFE is fairly easy. It cuts like butter, actually, but there are precautions that have to be taken into account. PTFE has a very high thermal conductivity, a very low thermal conductivity, so that the cutting tool, as it generates heat in the cutting action, the PTFE will not absorb that heat. It's all absorbed by the steel cutting tool, which then could lead to premature failure. So it is highly recommended that a coolant be used in turning and milling PTFE for that reason. PTFE also, in its sintering and molding process, could develop stresses. This can be alleviated by a second heat cycle, not up to 700 degrees, but up to something like half of that, and slowly cooled to relieve the stresses. A couple of other processes I'd like to talk about are the isostatic molding process. This is similar to compression molding, except instead of the PTFE being squeezed in this direction, it's squeezed against a steel core. This is done by, instead of having an outside steel core, the outside is a rubber bladder. Outside the rubber bladder is a chamber filled with liquid, like a transmission fluid, and outside that is the steel housing. When everything's capped off, the pressure is applied to the liquid, which forces it against the PTFE, against the steel core, and you get your compression that way. After this process, it then can be taken out, put in the oven, sintered, just like the other compression molding product, and then it too is ready to be machined. PTFE sheet is often made by the skiving process. Going back to the compression mold, we compression mold a billet and then put it up on a slow rotating lathe-like machine. And then a blade comes in as the billet is rotating, a blade comes in and skives off sheet that is taken up on a roller. The sheet is used to make stamped into gaskets, as you saw in some of the slides before. All kinds of applications. A very inexpensive way of making this product. If we go even thinner and make the Teflon tape that I was talking about to make the dental floss or to make the wiring harnesses and the wiring installation, this is done by a calendaring process where there's a progressive thinning of the, starts out as a plate, thinning down to, I think it can get down to as low as 1.5 to 2 thousandths thickness. This then can be slit into various widths, rolled up on a spool, and sent to the end user, who then manufactures it into the product that it needs to be it dental floss, filtration fibers, what have you. This, like I said, is PTFE in the virgin form, the unfilled form. There are also many minerals that can be added to PTFE to enhance its properties. We will look at some of these briefly. Glass is used to harden PTFE. The bridge slide bearings I was talking about earlier use a glass-filled PTFE to give it that strength. Molybdenum disulfide is used to give PTFE more lubricity. I know I talked about PTFE being a very low coefficient of friction, but molybdenum disulfide makes it even slicker for uses in bearings and seals and so on. Bronze is often put into PTFE to, again, give it strength and hardness. Graphite is another ingredient used to add to lubricity. This basic shape that I'm showing you here has graphite put into the PTFE to give it that color, but also to give it added lubricity when it's machined into usually a thrust bearing or something like of that nature. Carbon is put into PTFE to again give it hardness properties, increase its tensile strength. We also can put color pigments into PTFE. This is generally used for identification purposes. You can see that this lavender shaped color was put into this tape at the initial process, and then as it went through the coloring process, it got to this thin sheet. It's kind of hard to see it here, but these are probably several hundred layers of thin sheet wrapped onto that spool. Another product that you don't see on your screen, another additive I'd like to talk about for a minute, is the liquid isopar that can be added to Teflon. Put it into the blend, and as this isopar and the Teflon is put into the sintering cycle, this isopar evaporates, and what's left is a porous PTFE or a breathable PTFE. One such product that makes use of this is a vent cap to be put on top of an automatic transmission, automobile's automatic transmission. This will allow the venting of fumes. It's porous enough to allow the venting of fumes, but not so porous that in the case of a severe flood, water would not enter the transmission, or in the case of a rollover, the transmission fluid would not escape. So I hope to have given you much more insight into this wonderful discovery, this PTFE that was discovered by Dr. Plunkett back in 1938. I'm sure he did not envision near what this stuff would turn out to be. It's very versatile. Design engineers and applications engineers are constantly looking of new ways to use this stuff. I mentioned outer space. I didn't mention, but our astronauts' spacesuits are made out of a PTFE product. So it's got tremendous versatility. I thank you very much for listening, and now I will turn it back over to Jim.
Thank you for that informative presentation. We have a few questions waiting from our attendees. The first one asks, when would PTFE be a good replacement for metal?
Well, that's a good question. Application engineers and design engineers are always trying to lighten things up. They look at PTFE as a possible replacement for metal where they're trying to save weight. Sometimes the stiffness of PTFE does not allow that. But oftentimes, and more oftentimes than being a direct replacement for metal, PTFE is used in conjunction with metal. You saw a slide on this during my presentation, but I'll show you a little bit closer here. This is a gasket with a metal mesh liner that gets sandwiched in between two pieces of PTFE and then pressed and centered to give the strength of the metal as well as the protection of the PTFE. Also showed this during the presentation, metal energized spring. The PTFE by itself would not give enough sealing surface, but with the metal, it does. And if it was the metal alone, it would corrode. So it's the two materials complementing each other in that type of application. Also, PTFE could be used to save space. Thrust washers and sleeve bearings made of PTFE could replace metallic ball bearings. It really does, though, depend on the application.
Here's question number 2. Can PTFE be blended with other polymers?
Yes, it can. During the presentation, I showed you polymers being blended in with PTFE, but in those instances, the PTFE was the dominant, if you will, component, probably comprising of at least 75% of the compound. But PTFE can also be blended with things like PEEK, polyether ether ketone, a high temperature resistant thermoplastic that is also used because of its hardness characteristics as well as its high temperature resistance. But PTFE can be added to increase lubricity. Another material, polymer that uses PTFE is nylon. A small percentage of PTFE is added nylon for the same purpose, to increase its lubricity.
And here's question number 3. Can PTFE be welded?
Well, yes, but it actually has to be welded with a complementary type of material called PFA. PFA welding rods, if you will. 2 PTFE joints are put together, and then the PFA acts as the welding rod and the welding agent. This is used extensively in tank linings to protect steel tanks from corrosion, lined with the steel sheet, the Teflon sheet, and then the seams welded together with PFA welding rod.
And here's question number 4. Can I get PTFE to stick to anything?
Well, I said during my presentation that PTFE is impervious to all chemicals, all but one. There is an etching compound that we can apply to PTFE so that usually an epoxy can be adhered to it. The pump diaphragms I spoke of earlier sometimes use a rubber backing. The rubber is adhered to the PTFE by first etching with this ammonia etch compound the PTFE surface. It only affects the surface. It doesn't affect the integrity of the entire thickness of the PTFE, just the surface. And then epoxy can be applied to it, and anything, rubber in this case, the diaphragm, but also wood or what have you can be added, can be bonded to the PTFE.
And here's question number 5. Can you injection mold PTFE?
No, you cannot injection mold PTFE. The reason for that is that PTFE, as I mentioned during the presentation, is sintered or gels at 700 degrees. Much above that, it will start to degrade before it melts. In the injection molding process, the material is first melted and then fed into the mold cavity. This won't work with PTFE.
And here's question number 6. What are the downsides to using PTFE?
Well, there are some. I mentioned some of the difficulties in machining, the thermal expansion and contraction. Big consideration there. PTFE has a high rate of thermal expansion. If precautions are taken, that can be alleviated. Another downside of PTFE is its cost. In many instances, a cheaper polymer can be used. UHMW, for example, ultra-high molecular weight polyethylene, sometimes referred to as the poor man's Teflon, is a viable substitute for PTFE because it is much less costly. Other disadvantages of PTFE are, again, it's a plastic, so it can't have the stiffness of metal. Again, we've talked about ways that can be alleviated, but that is one consideration. It is still a plastic.
Thank you for taking the time to answer the questions and for providing some valuable information.
Thank you, Jim, and thank you for the listeners for listening in on this presentation and the informative questions that you've asked. I hope that you've gained a better insight into this material, and it's been a pleasure sharing this time with you.